Here we have the parameterization of a circle of radius a in the xy plane. The z-coordinate set equal to 0, and of course this is the parameterization of a plane circle. So we want to find the tangential and normal acceleration, so the component of the tangential component of acceleration. Remember, that's the change in the speed, which would be the derivative with respect to t, let's see, of the length of the velocity vector. The velocity vector here is minus a sine t, a cosine t, and 0. So this would be d dt of, let's see, the square root of a squared sine squared t plus a squared cosine squared t. And it's the same number multiplying sine squared and cosine squared. So if we factor it out and apply our Pythagorean identity, we just have the square root of a squared, which would be the absolute value of a, which is the radius of our circle, which is not changing. So there is no tangential acceleration. That means all of the acceleration is normal acceleration. So our normal acceleration will actually just be the length of the acceleration vector, right? Because it's normally the square root of the length of the acceleration squared minus a sub t squared. Okay, but if a sub t is 0, then this term doesn't exist, and we just have the length of the acceleration. So the acceleration is the derivative of the velocity. We've already found the derivative. We've already found the derivative position, which is velocity. So just do one more derivative. We get minus a cos t and minus a sine t and 0. So the magnitude of the acceleration would be the square root of a squared cosine squared t and a squared plus a squared sine squared t, which is the square root of a squared, which is the absolute value of a, which is the radius of the circle. So if you have a circular curve, right, so you have a circular path here, then we know that the acceleration is always normal. Now, if you're going around the circle this direction, let's see, and this points inward, right? And so it's all, this is the direction of the normal, and all of the acceleration goes in there. In fact, the magnitude is equal to the radius of the circle. So we have a vector that would be magnitude of the acceleration. It's long enough to carry you all the way back to the origin. So the magnitude of that vector is the absolute value of a, which is the radius. So with circular motion, all of the acceleration is normal. All of the acceleration is just turning you as you move around. As you move around the curve. So this is the case with the moon, right? We have the Earth, and the moon goes around the Earth in a very nearly circular orbit. So the moon doesn't speed up or slow down, right? The only acceleration there is the acceleration that comes from the force that is causing the moon to turn, right? It's the force of gravity that has the moon trapped here and forcing it to go around in this circular path. So we can definitely have motion when there's no speeding up or slowing down, right? We can definitely have motion where there's no speeding up or slowing down, so that all of the acceleration is perpendicular.